Good morning, afternoon, or evening to our honorable lecturers, as well as all my fellow students. Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Shalom, Nama Budaya, Salam Kebajikan, and Salam Harmony. Let me introduce myself. My name is Laras Nadya Wasundari, and my student ID is 2511021009. Today on this Tuesday, May 19th, 2026, I'm recording this comprehensive presentation video to fulfill the evaluation requirements for our course focusing on a deeply critical and fundamental topic in the digital and instructional landscape. That is computer networks, concept, and variation. The primary goals of this presentation are not only to measure our conceptual understanding of networking system, but also to train systematic idea delivery, particle media creativity, and critical, reflective thinking regarding how these network structures can be leveraged to support modern digital learning environments. To maintain a structured and logical flow, this presentation will strictly map onto the conceptual mind map that I have prepared for this topic. So before we deep dive into the technical definitions, let us first analyze the structural roadmap of my understanding through this conceptual mind map. As displayed on the screen, my cognitive framework from this topic is accord on a central core node, basic concept, and variation of computer network. From this central node, my understanding breaks out into five structural, interconnected pillars that will guide our lecture today. The first branch at the top left covered the, the basic concept of data communication, detailing the exact mathematical and physical pillar of sending information. Moving clockwise, the second branch covered network models, specifically drawing a stark, comprehensive between peer-to-peer and client-server architecture. The third branch at the top tried structural topology, which outlined the geometric rules governing the device, connection layouts, and the last one, it's not last, the fourth branch focused on geographical scale, breaking down the covered metric from localized building environment up to global interconnected system. Finally, the fifth branch, at the top left outline hardware and media, identifying the physical components required to maintain a stable digital transmission link. Let us begin our exploration with the fundamental definition of networking. As outlined in our presentation agenda, our technical exploration will move systematically through three core operational phases. The first, we will explore basic concept, unpacking definition, element, and operational reason behind establishing a network. The second one, we will analyze network variation, distinguishing between peer-to-peer and client-server system, along with their distinct operational conferences. The third one, we will inspect the underlying infrastructure, looking at physical hardware, evolutionary, transmission media, and and artic I'm sorry, and architectural topologies. Let us address to the fundamental question. What exactly constitutes a computer network? It is absolutely a sense. A computer network is defined as the international connection of two or more independent computing devices through a physical or logical transmission medium. The core driving catalyst behind this engineering is the principle of mutual exchange. From an educational standpoint, we establish this connection for three vital operational benefits. From an educational standpoint, we establish this connection for three vital operational benefits. The first one is resource sharing. This enables the highly efficient and cost effective sharing of data files, application, software, and critical physical hardware. For instance, in an educational media lab, instead of deploying 30 individual printers for 30 workstations, we connect a single high-end printer to a local network, allowing all users to access it seamlessly. The second one is communication. Network empower user to transmit instructional materials and collaborate across multiple digital media channels, including electronics, mail, real-time video reference, and specialized academic news group. And the third one is interconnection. It establishes an undivided architecture where multiple local workstations can tap into a single high-speed gateway to access broader public information structures. And next one, to understand how a network functions, we must look at the underlying data communication system. Any data communication system Any data communication event requires for non-negotiable operational elements. Fir- First is communicator, which represents the source node or device that package and transmit the initial data signal. The second one is the message, which compares the digital content, instructional material, or data packets being moved. Third is the media, which form the physical channels or electromagnetic spectrums pathway over which the data travel. Fourth is the communicate, which is the destination device designed to receive, unpack, and process the transmission. In terms of signal flow, this system operates via distinct transmission method. We have simplex system, which reference strict one-way communication channels where information flows in only one direction without a written loop. Like a classic example include traditional radio or television broadcast arrays. On the other hand, we have duplex system, which allows simultaneous bidirectional data flow, enabling both endpoints to transmit and retrieve concurrently. Much, much like a modern smartphone, telephone conversation, or a live video conference. To ensure that data does not degrade, get lost, or become corrupted across this channel, system employed robust data encoding mechanism to guarantee absolute reliability and data integrity from sender to receiver. Next, when evaluating network from an administrative or architectural perspective, we classify them based on their physical and geographical footprint. The most localized tier in the LAN or local area network, which typically spans an individual private office, a single building, or a school laboratory room. Architecturally, a LAN operates efficiently up to a maximum physical cable reach of approximately 100 meters. If a network engineer needs to extend connectivity beyond this 100-meter baseline, specifically hardware known as repeater must be installed to prevent signal attenuation and maintain data packets. Moving outwards, we have the MAN or Metropolitan Area Network, which scale up to cover a geographical radius of 10 to 50 kilometers, making it ideal for connection multiple corporate or university campus office distributed across a single metropolitan city. On an even broader scale, we anchor the one or wide area network, which spans immense geographical distance, frequently crossing national borders, boundaries, and entire continents. At the pinnacle of this scale sits the global internet, which represents the ultimate massive interconnected web of completely diverse networking and computing systems worldwide, communicating seamless by adhering to undefined standard open protocol suite known as TCP or IP. Now, let us examine our second core agenda item. Is network variation. This brand determines how administrative, authority, and operational roles are distributed among connected devices. The first variation is peer-to-peer network model, commonly abbreviated as P2P. In a P2P architecture, every single computer connected to the network holds completely equal operation, status, and administrative rights. There is no central authority or dedicated master server. Instead, every node acts simultaneously as both a client that requires data and a server that provides resources to other nodes. Because of this decentralized architecture, a P2P system requires no dedicated network administration, and the overall network continuity is highly resilient because it does not depend on a single central point of failure. If one computer shuts down, the rest of the network continues to communicate uninterrupted. uninterrupted. This model is highly practical, cost effective, and easy to set up for simple localized tasks. In our daily digital interaction, we see P2P system in action when we make a direct WhatsApp video call or link to personal laptops together via an access point or cable to rapidly exchange file data. In sharp contrast to the decentralized nature of P2P, we have the client server model. This architecture is built on a strict operational hierarchy characterized by centralized management. In this ecosystem, standard user workstation, known as clients, must route all their requests through a centralized high specification server computer. Because the server is tasked with managing intense workloads such as validating user logins, controlling network traffic, hosting massive database system, and distributing shared files, it requires a far superior hardware specification compared to client terminals, particularly regarding processor, clock speed, massive validated RAM capacity, and extensive hard disk drive arrays. Furthermore, their server, their server operates on a distinct class of network operating system, such as Windows Server platforms or specialist enterprise Linux distribution. A defining requirement of this model is the allocation of a decent network administration. The administration holds centralized control, utilizing specialized software tools provided by the network operation system to manage user credentials, monitor real-time data bandwidth traffic, enforce cybersecurity parameters, and perform systematic data backup from a single secure location. When we analyze this compression table directly, we can see that choosing between P2P and client-server architecture involves clear engineering trade-offs. Centralization and security. P2P distributes data across all endpoints, meaning security parameters are weak and must be manually configured by each individual user. Client server centralize all data and access right onto the server, providing controlled, highly reliable, and easily auditable security. Financial and technical costs. P2P is exceptionally inexpensive because it utilizes basic built-in operation system features without requiring specialized software or high-end central machine. Client-server influence a step initial financial investment to purchase enterprise-grade server hardware, appropriate server software license, and to maintain a professional administration on the payroll. Next is scalability and performance. Sorry, P2P performance decreases rapidly as the number of connected nodes increases because individual machines become overwhelmed handling both user, application, and network-related tasks. Conversely, the client-server model handles large-scale operations smoothly, offering rapid access speed and simplified backup routines because all vital educational assets reside in a central location. Now, let us advance to our third structure pillar is infrastructure and architecture. To translate this concept into functional reality, we must deploy specific physical hardware components. The first critical component is the NIC or Network Interface Card. The NIC is a hardware circuit board embedded into a device motherboard that acts as the essential physical gateway, converting internal computer data into signals that can be transmitted across a physical wire or wireless wave spectrum. Next, we utilize data routing equipment like hubs, switches, and routers. A hub is a basic device that simply relays incoming data signals to all connected endpoints. A switch is been a more intelligent evolutionary step, filtering and directing data traffic explicitly to the intent destination node, thereby optimizing local bandwidth. A router is an even more advanced pieces of equipment that manage data flow across entirely separate network structures, often combining the functions of a hub, access point, and repeater into a single unit. Finally, we must arrange this device according to strict geometrical layouts known as physical topologies. Network engineers choose between distinct topological rules based on the needs of the environment. We can deploy a star topology where every node connection directly to a central switch. I'm sorry. A ring topology where cables from a continuous security loop to prevent data collisions. A bus topology which utilizes a single central backbone cable or highly reliable mesh topology where devices are cross-connected to create multiple paths for total fault tolerance. The final piece of our infrastructural puzzle is the transmission data, which has gone through a fascinating technology evolution. We begin with traditional copper-based interest wiring system, which utilize twisted pair cables terminating in standard RG45 socket to move electrical signals across local environment. As mobility demands grew, we saw the rapid rise of wireless technology. Wireless network completely eliminated physical kinking cables, instead broadcasting data over the air. the air using high frequency radio waves, microwaves, or locates in phase light directed through the strategic access point. Today, our modern high speed data demands are powered by fiber optic technology. Fiber optic replaces copper entirely, utilizing that utilizing ultra-pure standards of flexible glass or specifically plastic to transmit data over immense distance at the speed of light using digital light pulse. This breakthrough provides massive signal bandwidth, smaller physical footprints, and complete protection against electromagnetic interference. So, we have reached the final stage of our presentation, conclusion and reflection. To summarize our journey today, analyzing computer network demonstrated that there is no single perfect network design. Instead, deep comprehension of network operation and infractional skills empowers us as technology professionals to choose and implement the exact right architectural configuration based on specific financial budgets, geographical permanence, and communication efficiency needs. As an undergraduate student in educational technology here at Unixa, my critical reflection on this matter goes beyond the technical definition of cable, switches, and server. I realized that computer network from the literal, non-negotiable foundation of modern collaborated learning. Whether we are designing a simple P2P connection for a localized smart classroom or configuring a massive client server infrastructure to host a university-wide learning management system. We are constructing the digital pathway that democratizes information access and enable interactive international models. Understanding this infrastructure ensure that we do not merely remain passive consumers of the educational tools, but instead become component architects capable, capa- capable of building robust, structures, and highly scalable digital learning environment for the future of education. That formally concludes my video for the, that formally concludes my video presentation for today. I hope this lecture has been structured, logical, and illuminating. Thank you very much for your time and all viewers for your gracious attention. Santi Santi Om. Wassalamualaikum warahmatullahi wabarakatuh. Shalom nama budaya, salam kebajikan, and salam harmoni.